So suppose we want to prove a non-trivial claim about set equality. In this example, we have three sets, A, B, and C, and we want to show that A minus B union C must equal A minus B intersect A minus C. We can think of this as a kind of a distributivity property of minus over union. So how do we go about proving something like this? We know that two sets are equal just in case they contain the same elements. So that's what we've got to prove. We prove one direction, that if X is in the first of these sets, then it must be in the second one. And then we prove the other direction, that if it's in the second one, it must be in the first. And then we can use universal generalization to say, well, if this is true of some arbitrary value X, it has to be true of all values. And then we've got the proof that we need. So let's look at how we do this. We're going to start the first direction. We're going to assume as a conditional premise that X is an element of the first of the sets. And then imagine through some process labeled ... here, we're able to derive the claim that X is an element of the second set. Suppose we can do that, then how do we finish the proof? And we'll come back to that. We'll use conditional discharge to show that if X is in fact in the first set, it's in the second one. And then what we'd like to be able to do is to say, and we know the other way also. I put this in green because we'll be able to say that if every step that we used in doing this is in fact reversible. If it's not, we have to do a separate proof. And I've written it in green. We're hoping it's going to turn out that that's so. We haven't seen the steps yet, so let's be careful. Assuming we can do that, then we say we've got that being in set 1 implies 2, being in 2 implies 1, and by the definition of equality, if we've got two directions, we've got a definition of equivalence, then we've got equivalence. So the claim that X is in one of them is equivalent to the claim that it's in the other of them. We can use universal generalization to say, well, then it has to be true for every value, if it was true for this arbitrary one. And then we can say, well, the definition of set equality is that you're equal just in case you contain the same elements. So this is our proof, but the guts of it go here. How do we do that part? So let's focus on that. All right, and recall that a way to do it is to take our starting claim, X is an element of this set, use the definitions of the set operators to convert this into a logical claim that uses Boolean operators. Then we can use what we know about Boolean logic to manipulate it, and then we should be able to come back. So we'll use the set definitions, in this case, of set difference and union, because those are the two we use. We'll derive this claim. We'll see how in a minute. It takes a couple steps. But now you can see that we've got logical operators and, not, or, so forth. We can use Boolean reasoning, and we're going to get this claim. And we can then use set definitions again, in this case, difference and intersection, and we'll get the claim that we want. Okay, so now we just have to fill in the pieces of that. So let's see how that works. All right, so that's what we want to prove. We start with our conditional premise. We want to end up with this, and then we'll be able to fill in the rest. So how do we do it? We use first the definitions. So the definition of set difference tells us that if X is an element of the difference between these two sets, then it's in A, and it's not in B union C. And now we need to get rid of that union, and we know that that means if X is in the union of these two guys, then it's in B or it's in C. Now we have an expression using Boolean logical operations. What should we do next? Now is where we have to design our proof. And we could use any of the Boolean operators that we've got. So how do we decide? A standard thing to do is to say, let's use De Morgan here, because if we look at the goal, we look at where we eventually want to be, we're talking about claims that don't have a not outside a long expression. So let's use De Morgan to get rid of that not at the outside. All right, and we're using logical De Morgan here, and so we push the not through, and we have not X is in B and not X is in C. Okay, now we have to decide what to do next. And a thing we could think about is this. Look at the goal. Here's the goal. There are two mentions of A and one each of B and C. But if you look at what we had up here, we had one mention of A and one of B and one of C. We need another mention of A. And we're thinking, how do we do that? So we do a step that maybe seems silly, but it gets us towards our goal. Idempotence tells us that if we've got X as an element of A, then we can have, in fact, if we have any claim, we can have that claim and itself. Changes the truth value not at all. So we're going to add a second mention of A. X is an element of A and X is an element of A. Now we have two A's, a B, and a C. They're not in the right order, so they're not in a way that's likely to make it easy to derive what we want. So let's basically move them around. In order to move them around, we're going to have to do some associativity, right? We've got these two associated and those two associated. We're going to want to flip. So first let's do some associativity, and let's group A and B together. Now we need to get the B mention over here near the first A mention, and so we can use commutativity to do that. All right, now things are in the right order. A, B, A, C matches A, B, A, C. They're not associated correctly, but we can fix that. So now we have a mention of A and B and another mention of A and C, and now let's see if the mentions get us what we want. At this point, let's reverse our process and go from logic back to set operations. And I showed two steps here together because we're going to do set difference in both of them. We have X as an element of A and not B, and using the definition of set difference, that says it's in A minus B. And similarly, here we have X as an element of A and not C, and so we use set difference a second time, and we get that X is in A minus C. All right, now we're looking close, but we've got a logical and we need a set intersection. So we use the definition of set intersection. You're in the intersection of two sets just in case you are, in fact, in both of them. So we filled in that last justification. And now we fill in the rest of the structure, except that notice that I've left this one line blank. And recall that's where we would like to argue that we've got the other direction. That if you're in that set, you must also be in that one. And I'd like not to have to actually prove it. So I'd like to argue that every step along the way here is, in fact, reversible. And we look at what we've done. We've used definitions and we've used identities. And those are all reversible. So we can correctly claim that our proof is reversible, at which point we say, fine, then the claim that X is in one of the sets is equivalent to the claim that it's in the other one. We generalize to any X, and we use the definition of set equality, and we're done. So the key here is that we've got the structure that's easy. When you do a particular proof, you've got to look at how to choose the operations. And a good strategy is, we'll call it eye on the prize. What is it that we're trying to get to? How do we manipulate what we've got to get there? And that's how we picked idempotence there.